Okay, this is David Zierler, Director of the Caltech Heritage Project. It is Thursday, February 10th, 2022. I'm delighted to be back with Professor Alexei Kitaev. Alexei, it is good to be with you again.
Thank you.
Alexei, today I'd like to start in the year 2012 with something that you might consider an interesting question. So, you were part of the inaugural class of Breakthrough Prize winners. So, first, did you ever know Yuri Milner before the prize was announced?
No,
You never met him before.
no.
Now, here's where I think I'd be very interested to hear what you have to say about this. So, if you look at the list of the people that you shared the Breakthrough Prize with, so first there's Alan Guth, and there, of course, it's cosmic inflation, something that there are very exciting possibilities about an experimental or observational demonstration that the theory of inflation is correct. Andre Linde, of course, about the multiverse and what he believes is a testable proposition, that the multiverse is something that we could put to the rigors of science. Then when you look at Nima Arkani Hamed, Maxim Kontsevich, Juan Maldacena, Nadi Seiberg, particularly Ed Witten, all of them are related to string theory. And of course, there are things in string theory that we are waiting to be experimentally validated as well. I wonder where you see quantum information in this regard. In other words, to the extent that the Breakthrough Prize awards excellence in physics, even though there might not be the testable demonstrations that, for example, the Nobel Prize Committee is waiting for when they award a Nobel Prize. I wonder if you can reflect on that, what your thoughts are.
Uh, Regarding testable demonstrations, I think quantum information is easier, although there hasn't been a testable demonstration of a quantum computer that would solve some real problems. By now, there has already been a demonstration of basic principles, and there is no reason to doubt quantum mechanics. And quantum mechanics, which was discovered almost 100 years ago, implies that all these things are possible. So to me, there is very little doubt about the possibility of a quantum computer. It's just a difficult experimental and technological task. So this is not answering your question. Maybe I'll mention it later regarding a possibility that quantum mechanics might be incorrect. But if we set this aside, then the difference is quantum information or quantum computing is a kind of applied science, and the other work you mentioned, like string theory, is more fundamental. That's the main difference. But on the other hand, the novelty of quantum information science was that before, say, 1980s, people didn't try to think about quantum mechanics in a complex setting. They think that there are natural processes, the laws of nature cannot be changed, and the systems they study are also given. And the problem is to infer some parameters of that system from experimental data. And quantum information is about making complex quantum systems and controlling them. And they may exhibit some new phenomena that were not possible in natural systems. And this is a novel aspect. And It appeared not in my work, it appeared in the work by Bennett, Feynman, and others. And Peter Shor basically created the foundation of quantum computing. He showed how to correct errors, and that enables computation on large scale in principle.
Alexei, you mentioned the expectation or there being a benchmark that we need to have a quantum computer that has some social utility or usefulness. To what extent is that a fair expectation, certainly in light of the fact that, depending on how you define it, we do already have quantum computers, even if on a very small and not particularly useful scale today?
Sorry, I didn't get the question.
So the question is, if there is an expectation, whether it's from the Nobel Prize Committee or by corporations or society at large, that for there to be an experimental demonstration of quantum computation, that the expectation is that the demonstration needs to show that the quantum computer is somehow socially useful. And of course, we're not there yet. But we do have quantum computers on a very small scale, at least with a few qubits.
Well, I don't know who has this expectation. I think the expectation comes from the fact that people are not exactly interested in quantum computing. They are interested in things that can be done with the quantum computer, and this is very natural. So it's not about the demonstration of principles. People just want to see it working, and that's it. Yeah, and I also share this expectation because, as I said, to me, there is no doubt that the foundations are solid, and if everything is done correctly, it will work. But I still want to see it actually work.
Alexei, for your own research, more broadly defined in quantum information generally, do you see any of the research, theoretically, that has been experimentally or observationally demonstrated?
Regarding my research?
Correct.
Well, this is a good example. Surface codes has been constructed by the Google group, and they have been demonstrated to work. But on the other hand, it's a mathematical construction, so there is nothing that can possibly fail in the construction itself. It's more like application of this construction in practice, and I'm very happy that it happened.
Alexei, we'll return to some non-technical questions. We'll also cover some of your key papers in the last 10 years. So in 2013, the paper An Area, Law, and Sub-Exponential Algorithm for 1D Systems. First, what is a 1D system? I assume a one-dimensional system.
Yeah, it's a one-dimensional system. In this case, we consider one-dimensional Hamiltonians. There are some units like spins or maybe other simple systems with a small number of quantum states, and they interact with their neighbors. So they're arranged in a sequence, in a chain, and nearest neighbors interact.
And as you note with your co-authors on this paper, it improved exponentially the results from Hastings. What was Hastings' result, and how did this work improve upon it?
It's a mathematical physics result. It's a statement about ground states of certain Hamiltonians. As I said, the Hamiltonian involves interactions between neighbors. And there is another technical condition, the existence of an energy gap, meaning that excited states have some smallest energy. One cannot create an excitation with an arbitrary small energy relative to the ground state. Hastings proved that if we cut the system in half and calculate the entropy of one half, this is called the entanglement entropy, because the whole system is in a pure state. Its entropy is zero, but if we consider half of the system, its entropy is finite. And Hastings obtained a bound on this entanglement entropy in terms of the energy gap. He proved that the entropy cannot be larger than some function of the energy gap divided by the interaction energy, and some function of the number of states on each elementary subsystem, on each block of which this chain is built. So we obtained a beta bound, and now I don't remember whether we actually improved it exponentially or there was a previous work that improved it exponentially, and we improved it even further. Somehow I don't remember that.
Alexei, back at Caltech, were you involved in the creation of the IQIM? In other words, the transition from the IQI to the IQIM?
No, I wasn't involved in any organizational things at all. And well, I recall how the transition occurred, and there was, of course, a proposal, and I participated a little bit in writing this proposal, but most of the work was done by other people. I wrote a few paragraphs regarding what I was going to do.
Alexei, perhaps in your discussions with John, or more generally your appreciation of what was going on at the time, why this time period, 2011 to 2013, what was going on in the field of quantum information that suggested the time was right to add matter to the IQI? What did that mean for the field?
Well, of course, this is useful for the field because we're interested in doing complex quantum experiments with various systems. And I mentioned last time that quantum optics and cold atoms were the first systems on which complex quantum experiments were done. But we're also interested in doing this in condensed matter systems. And people naturally had started that before IQM, but getting more funds for such work is important.
Alexei, in 2013, with Peter Brooks and John Preskill, you wrote a paper, Protected Gates for Superconducting Qubits. So what are protected gates? And are the gates doing the protecting, or are they being protected?
They are protected in the sense that they're designed in a certain way such that errors that might occur during the implementation of the gate does not affect the result very much. So in this sense, they are protected.
And the focus on superconducting circuits, do you see from this work a particular connection with certain industries that have approached quantum computers from a superconducting circuit perspective?
Superconducting circuits, it's one technology. It's an alternative to cold atoms and ion technology. And those circuits are built of elements like Josephson junctions. It's the most important element. And well, you mentioned industry. Right now, Google is building a quantum computer using superconducting circuits, but it's good that they have enough resources to build large enough systems and to do complex things. But people in various labs also do that on a smaller scale.
Do you see superconducting circuits as the most plausible approach to building a scalable quantum computer?
I don't know. I'm involved in the work of Google, so I hope superconducting circuits will be the most viable approach, but I cannot tell.
Do you have a sense of why Google adopted this approach as opposed to trapped ions?
I don't know, but the Google group was initially led by John Martinez, who was specializing in superconducting circuits. I don't know. It just happened this way. I don't know.
Alexei, in 2015, you won the Dirac Medal. I wonder in what ways this recognition was meaningful to you, particularly in light of Dirac's fundamental contributions to quantum mechanics and that relationship ultimately to quantum information.
Sorry, somehow I got distracted.
That's okay. So in 2015, you won the Dirac Medal. And I wonder if you thought about in what ways that might have been particularly significant for you, given who Dirac was and his contributions, his fundamental contributions to quantum mechanics.
Yeah, of course. I'm very honored to receive the Dirac Medal. Yeah, it was nice to travel to Trieste and participate in the ceremony. But the Dirac Medal is a prestigious award, so I'm proud to receive it.
We talked earlier about Richard Feynman's ideas and how they led to quantum information, the field. Do you see that going back even farther? Do you see an intellectual connection that goes as far back as Dirac, for example?
No, I don't. Regarding quantum information, Feynman was one of the first people, except Yuri Manin, he was the first to consider this idea that quantum mechanics can be useful for computation.
Alexei, in 2017, efficient decoding for the Hayden-Preskel protocol, where you looked at Hawking radiation. So first, what is the Hayden-Preskel protocol?
Hayden-Preskel protocol, it's a bit difficult to explain. It's basically recovering information from a complex system where information may be scrambled. And Hayden and Preskel made a nice story to introduce the problem, and it involves black holes. And the problem goes that Alice wants to hide or destroy diary containing private thoughts, and Bob is trying to spy on Alice, and Alice thinks that a black hole might be the safest place to get rid of her diary, and she throws it to the black hole, but Bob can, in principle, recover the information from the Hawking radiation. Indeed, there are many interesting information theoretic properties of black holes, but this particular task is not related to black holes specifically. It's about any complex system. Suppose we perturb a complex system a little bit, and we can think about a piece of metal at a certain temperature, and we do a small perturbation. Maybe we send a laser pulse that hits it a little bit. Maybe we just touch it. So it's a small perturbation to the system, and any effect of that perturbation quickly dissipates. And if some energy is added to the system, it is only reflected in the temperature. The system heats up a little bit. But the actual information seems to be lost. In principle, if it's a quantum system, one can decode its quantum state and recover the perturbation that happened. But suppose we don't have full access to the quantum state. We can only access a small piece of the system. Then the recovery is not possible. However, Hayden and Preskel noted that if this quantum system was previously entangled with another system, such that we fully control that second system, can do arbitrary manipulations on a quantum computer, for example. Or we may say that the original system was entangled with qubits in a quantum computer. Then, using those qubits and a little piece of the system itself, we can recover the perturbation. So this, Hayden and Preskel showed that it's information theoretically possible. And Benny Yoshida and I just gave an algorithm. It's a quantum algorithm, how to recover the information.
Alexei, was this the first time around 2016, 2017 with the Hayden-Preskel protocol? Was this the first time that you started thinking about black holes and Hawking radiation, or is this related to earlier research at all?
It's related to research that I did a little earlier. Of course, I have been always fascinated by black holes, and the Hawking information paradox is one puzzle that bothered me, and I knew about that a long time ago, and the work by Hayden and Preskel was very exciting. Of course, it didn't solve the paradox, but it shed some light on how black holes might work. So I started thinking about this problem seriously, I think in 2014. And as a result, I came up with the SYK model and maximal chaos in the SYK model. That was in 2015, but I started working on it in 2014.
And to clarify, Alexei, are you thinking about black holes purely as mathematical constructs or as theories, or is there something going on observationally with real black holes? For example, were you following developments with LIGO, or did you ever talk with Kip Thorne about black holes?
I have followed the developments of LIGO to some extent, and it's very exciting that people can see actual signals from black holes. The black holes I study are kind of toy black holes, not much related to the real black holes. So my actual interest is rather theoretical, rather abstract. But I'm still excited about the LIGO developments in astrophysics, because there are so many interesting things happening in the universe, and it's very exciting to learn about that.
Alexei, to clarify further, does a toy black hole mean that for the purposes of your theoretical work, it could behave in ways that are different than a real black hole?
It behaves differently because one can make it respond in a certain way, which we cannot do with a real black hole. A real black hole is big, and if you look at the formulas for the Hawking radiation, the Hawking radiation is negligible. We cannot see it in practice. Furthermore, I'm interested in more subtle properties than just Hawking radiation, like finding complex correlations in the Hawking radiation. And that's completely impossible with a real black hole. So I'm thinking about those toy black holes, which are just mathematical models sharing some properties with the real black holes, but actually quite different.
Alexei, yet another prestigious prize. In 2017, along with Xiaogang Wen, you were the winner of the Oliver Buckley Prize in Condensed Matter. So first, did you work at all with Wen?
No, I've never worked with Wen.
What does the Buckley Prize for you, what does that say more broadly about the connections between condensed matter physics and quantum information?
Well, I can say what I did and how they're connected in my work. I was interested in quantum codes, and I realized that certain condensed matter systems can encode quantum information such that it is protected from errors. They effectively work as quantum error correcting codes. And these systems have non-trivial topological properties, and they carry excitations called anyons. In particular, one could try to use quantum Hall systems. Fractional quantum Hall systems are known to carry anyons, although anyons are hard to observe experimentally. And there are other systems with non-trivial topological properties that can also be used in principle to encode quantum information. For example, Majorana wires. These are very thin wires made of certain semiconductors in contact with a superconductor and in a magnetic field. And they feature boundary Majorana modes. At the end, at the ends of those wires, there are some special. I wouldn't call them particles. These are Majorana modes. It's a special place that hosts part of a quantum state. The quantum state is actually in the whole wire, but one can access it through the end. And this can be used to store a qubit. The whole wire can be used to store a qubit. So this is another interesting condensed matter system. So the Buckley Prize I received for my work on such systems, topological quantum systems, and also my other awards were for this work and its connection to quantum information. So I studied topological quantum systems, and when also studied topological quantum systems, he started earlier than I, but he didn't make an explicit connection to quantum information, as far as I know. In his later work, there was a connection. He and Levin wrote a paper similar to our paper with John Driscoll. I mean, they derived the same formula for the topological entropy of a disk in a two-dimensional system that carries anyons.
Alexei, we've talked previously about the SYK model in 2017, along with Josephine Saw, the soft mode in the Sachdev-Ye-Kitaev model, and its gravity dual. So first, to understand, did you ever work directly with Sachdev and Ye, or did you modify their work independent of them?
I modified their work independent of them.
And what were the opportunities? Where did you see need or opportunity to modify or even improve upon what they had done?
The story is this. I mentioned in 2014, I started thinking about information in black holes. And I realized that one can first, there is something interesting about black hole horizons in connection with quantum information. And second, one can access the black hole horizon from the outside if one studies so-called out-of-time order correlators. And so I was looking for a model where out-of-time order correlators would be similar to those in black holes. But the system itself could be quite different from a black hole. And I had some understanding what kind of system it should be. And I was looking through the literature and just looking for an interesting system that might be good for that purpose. And I came across the paper by Sachdev and Ye, and that system seemed promising, but it was also rather complex, so I figured how to simplify it. So I came up with a slightly different model that shares some interesting features, but is easy to study. And then I calculated the Lyapunov exponent, how fast those out-of-time order correlators grow, and found that it's the same number as the same function as in black holes.
And the soft mode in the SYK model, what does that mean? What is the soft mode?
A soft mode it is a general concept in physics. When we build a many-body system, or it can be some natural system in particle physics, there are excitations with high energy and low energy, and soft modes are basically excitations with low energy, excitations that are easy to produce. Soft means it's easy to deform the system. the energy required for that is much less than the elementary interaction energy in the Hamiltonian.
And what are out-of-time order correlators? What is out of time?
When we make an observation on a system, we first perturb the system and later measure the effect of that perturbation. Such an experiment can be mathematically described by a response function, and it's also related to a correlation function between operators. And usually when we consider such a process and construct the corresponding correlation function, the times on the operators go in a certain order. Usually the times increase and then decrease. For example, A of 0, B of 1, C of 1, D of 0, something like that. So there is a certain sequence of times that enters the expression, and it goes first forward in time and then backward in time. Essentially, it's a double. For some technical reason, it has to be doubled, but the natural evolution goes forward in time. And an out-of-time order correlators is where a time scale can alternate, like 0, 1, 0, 1. And such correlators do not appear in any expression for a naturally observable quantity. It's related to things that can be observed if we actually reverse the direction of time, which has been done, by the way, by Google. They studied certain quantum evolutions, and then they ran the same evolution backward. And in the meantime, they introduced some perturbation. And when running the evolution forward and backward, and doing a measurement, we can see some new things, and they're related to out-of-time correlators.
Alexei, another collaboration with Josephine saw the following year statistical mechanics of a two-dimensional black hole. So to clarify, is this also a toy black hole that you're thinking of, and that's why it has two dimensions?
Yeah, it's a toy black hole. Yeah, exactly.
And how do you apply statistical mechanics to black holes? What does that mean?
Statistical mechanics studies properties of a system at a finite temperature. And we just considered this black hole at a finite temperature. Now, black holes should be considered at a finite temperature. It's the Hawking temperature. They have a natural temperature associated with them that depends on their energy. So this is not special to the toy black hole. But of course, two-dimensional black holes are special, and we considered a simple model and solved it.
I suppose if it's a toy black hole, it can be any number of dimensions that you want. How many dimensions are in a real black hole?
In real, it's 3 + 1, 3 spatial dimensions, and 1 time dimension. So it's 4 dimensions. And the black hole we considered with Sach was 2-dimensional in this sense.
And the reduction to 2 particles in the anti-de Sitter space, what are the 2 particles?
Oh, it's quite technical. It's just a trick. First, we consider two-sided black holes, which do not occur in nature. These are artificial constructs. If we entangle 2 black holes, 2 identical black holes in completely different universes, but somehow they're entangled. This is called a two-sided black hole. And entanglement is a quantum concept, and if we think of them classically, they're connected by a so-called wormhole. So they share some part of space, but that region of space is usually not traversable. So one can enter it from either side, but one cannot go back unless you go back in time.
Alexei, we'll take a brief break from a technical discussion for a question that historians of physics are going to be very interested in. So if you look back 20 or 25 years, let's say when you were at Microsoft and the quantum information effort was very small and very, of course, theoretical, and then you fast forward to today, to 2022, and all of these major companies, all of these startups, worldwide effort, there's so much interest and input and excitement about quantum information and quantum computing. Between then and now, over these 25 years, is your sense more that the increasing interest and excitement in quantum information was gradual, or were there certain advances in the field along the way that created bursts of energy and resources that explains how we are where we are today?
To me, it looks like a gradual process. The technologies advance, and on the other hand, there is more funding, more interest to quantum information these days than in the year 2000. So now, indeed, many companies are investing in quantum technologies. I don't know whether it will be successful on the time scale that is relevant to those companies. In the end, it will be successful. I'm sure about that, but I don't know how soon.
Alexei, of course, you're not a business person, but to the extent that you understand why major companies, governments, and even startups are investing so much money for people that run the finances who are not specialists themselves, what is your sense of their motivations? Why are they excited about this? What do they believe makes this such a good investment, even if the investment will pay off many years from now?
I don't know. There are companies who really care about distant future, and they make long-term plans. But I guess in most cases, this is something related to their business that I don't understand. I mean, how finance works, how social effects work, and things like that.
If only passively, Alexei. In other words, not in any way that you have given a lecture where you're convincing people to invest in these technologies. How do you see your research contributing to people believing that this is an investment worth making?
I don't know. Well, I suppose that when people see this result about surface codes, they become more confident in quantum technologies. And surface codes is something that I worked on theoretically some time ago. Yeah. So in this case, it helps to make people confident in this technology.
Alexei, a question about collaboration as it relates to two recent papers: observation of time crystalline eigenstate order on a quantum processor and information scrambling in computationally complex quantum circuits. You are a collaborator with dozens and dozens of people on these papers. I'm curious if you see that that's a trend in quantum information, that significant papers are more likely now to be a major collaboration between tens or even dozens of scholars, and single author or dual author papers are becoming less likely.
These papers are written by people in the Google group, and they basically put all the names of all the people in the group. And for example, I didn't participate in the time crystal paper at all. I had some discussions regarding information scrabbling, so I might say something about it if you ask. But
please do. I'd love for you to say something about it.
Yeah. So this is related to out-of-time autocorrelators, and it's an experiment that was done using the Google machine with 53 qubits. The qubits are initialized somehow. Then we run a number of gates in parallel. Each pair of qubits is made to interact. Then we consider and run another sequence, another set of gates, and these are called layers of a quantum circuit. So we apply some number of layers, then we introduce a perturbation, an extra gate, and then we reverse the whole process. Except this one thing that is done after running a certain number of layers. And this perturbation, now suppose we do without a perturbation, we apply those operations and then undo them. And the system should come to the same state it was before, say all the qubits in state 0. But if there is a perturbation in between, then this perturbation will affect some qubits. And one can study how this perturbation spreads as a function of the number of circuit layers. And this kind of work was done experimentally, but there are several variations. For example, one can apply gates for which the system is not chaotic. And one can see that the behavior is different. And one can also calculate certain things theoretically, because this out-of-time autocorrelators are described by relatively simple theories. And other things in this paper that we had to compute theoretically were computed using numerical simulation. So basically, the average values were computed theoretically, and fluctuations around the average values were computed numerically. And the results were compared with the experiment. And we found, they found agreement, although the real system has a lot of noise when those layers of circuit are run and then reversed. The system doesn't quite come to the state it was before. It comes to a state that is correlated with the state that was before, and one has to modify the theory and take this noise into account to make a correspondence between the theory and the experiment.
Alexei, on the second paper, information scrambling, is information scrambling related at all to cryptography?
Information scrambling, no. I guess it could be related to cryptography, but the way we discussed it, it's not related to cryptography.
And as the paper notes, quantum scrambling can be very useful for physics research. I wonder what are some of the problems in physics for which quantum scrambling might be useful?
Well, it's just a theoretical problem one can consider, and while doing that, one could discover some interesting properties of concrete physical systems. I think it's useful in this sense. And I mentioned the SYK model. My logic was reverse. I was looking for a system with certain out-of-time order correlators, and I found one, but one could see how it could happen the other way around if one studies a system like the SYK model. It has interesting properties, but some very interesting properties are related to out-of-time order correlators. And also, I should say there are related models. There is a so-called Moldesani-Chi model that is two copies of the SYK model coupled to each other. And there's interesting properties related to actual correlators one could study experimentally if one is able to make the system experimentally.
Alexei, more recently, a very exciting announcement at Caltech. Dr. Allen and Charlotte Ginsberg are supporting a new quantum center here. Were you involved at all in that process?
No, I'm not involved.
Do you see any overlap with the IQIM or any possible areas of joint work with this new quantum center?
Yeah, sure. Yeah, of course. It's related to the same type of problem, so there should be coordination of activities.
It begs the question, why the need for a new quantum center? Are there ambitions with this center that are simply too large for IQIM to house itself?
Yeah, I think so, because although I am not involved in this, my general understanding is that this new center will allow to build new labs, and just using the IQM funding, it's not enough to build new labs. It should be something on a bigger scale. In particular, if it involves a new building, it's a very big investment. If it happens on this scale, it will be a totally new level of activity.
Do you see advances potentially there in labs experimentally that will be particularly relevant for your research?
I'm a theorist, so I think I'll just keep doing what I'm doing. But of course, I'll be glad to talk with people and see. Maybe at some point I will be able to help them with some advice. But as for myself, I'm a theorist. I'm focusing on what I can do well.
On the question of you keeping on doing what you're doing, your most recent paper, Two-Way Approach to Out-of-Time Order Correlators, what is some of your current work on out-of-time order correlators, and how does this relate to the SYK model?
We studied models like the SYK model. It's a class of models where there are some little systems interacting with each other. So in this class of models, just got a better understanding of out-of-time order probabilities. And again, it's a technical result. Two ways means that we solve some equations not forward in time or backward in time. We solve two sets of equations in counter-propagating directions, and then the final answer is obtained by combining these two solutions.
Alexei, also in 2021, you were elected to the National Academy of Science. What was that like, and what do you think that meant more broadly for the field of quantum information?
I don't know what it means for the field. For myself, I'm honored to be elected to the National Academy of Science. Yeah, so it's a recognition of my work. I see it this way.
Of course, this has all happened during the pandemic. Are there opportunities to travel to conferences, to meet other people in the academy that you're looking forward to doing?
I'll probably travel this year to Washington to participate in the meeting of the academy. But people travel these days, so I've been to several conferences.
Well, Alexei, now that we've worked up to the very present, I'd like to end our talk with some general retrospective questions, and then we'll end looking to the future. So one thing we haven't covered yet is your work as a professor, as an educator. Do you have opportunity at Caltech to interface with undergraduates at all?
I teach, right now I'm teaching quantum computation. So I interact with undergraduates when teaching some courses. I don't interact very much outside of this.
Now, as you well know at Caltech, computer science is now the dominant field or the major among undergraduates. Are the students who are interested in quantum computation generally interested in computer science, or are these more students that have a physics interest and that's why they're coming to you?
There are both types of people. There are more physics students than CS students, but CS students also are also interested. Some CS students.
And if undergraduates who are thinking about their careers and if they're looking for advice, are there jobs in quantum computation or quantum information that you see on the horizon in the way that, for example, computer science, of course, there's many jobs in that field?
Mm-hmm. Well, I don't know what to say. I cannot give any advice for a computer science student. For a physics student, yeah, sure, there are jobs that involve building a quantum computer. Like I said, at Google, Microsoft, IBM, and smaller companies. And I think for this, it's important to know both physics and some computer science. Yeah, it's an exciting field right now. I would also give a warning that it might not be funded, say, 15 years from now.
Right.
So.
We'll talk about that. It's an interesting question. Alexei, for graduate students and even postdocs that you've worked with, just generally over the years, what has been the value to you for your research in mentoring graduate students and postdocs?
What was the value for me to mentor students? I don't know. First of all, I have not very good at interacting with students. I have only had a few graded students in my career, so of course for them the value is just learning physics, learning how to work in the field. So I hope my mentoring helped them. But, other than that, I don't know. I'm a bit ashamed that I cannot do a better job, but I guess it's my personality. I'm not very good at interacting with people.
Alexei, very broadly conceived. We've touched on it, but a more direct question. So if you look at all of your contributions in quantum information, quantum computation, are there specific aspects of your work that you see ultimately as being most relevant to the creation of a scalable quantum computer?
Yeah, I mentioned surface codes. I think this is one piece that is practically useful.
Yeah, let's talk about that a little more. What is it about surface codes that you elevate above all the other things that you've done?
Because I see it implemented in hardware, and it's pretty easy to implement compared to other ideas. So it's I can what to say. One can think about the surface code as a code. So there are qubits, and there are some check operators, which one can measure. In this way, one can detect errors. And those qubits can be put on a plane such that those check operators are local. One needs to measure a combination of 4 qubits and get a bit 0 or 1. And if it's 1, it means that there is an error in some of those qubits. We don't know which one, but by combining such measurements, one can figure which qubits are in error. So this is the rough idea. It's a special type of an error correcting code that is relatively easy to implement. I had other ideas that might also work, but have not worked so far. In particular, the Majorana chain. The Majorana chain, I wrote a theoretical paper in 2000 where I put forward the basic concept that there is a one-dimensional system, and there are Majorana modes at the ends that are formed due to special interactions between the elementary block of that system. Later, around 2010, a few people, including Gil Rafael at Caltech, figured how to do it in a real material using a semiconductor wire with strong spin orbit interaction in connection with superconductor and in a magnetic field. And there has been a lot of work funded by Microsoft, but the work itself, partially it's funded in part by Microsoft, including the work of Leo Covenhagen on realizing those Majorana modes. And the first reports were in 2012. Unfortunately, it's still inconclusive. I mean, they see those Majorana modes, some signatures of the Majorana modes in the experiments, but the system is not clean enough such that one can tell for sure this are Majorana modes. It could be something else. It could be some effect of disorder. And making the system clean the hard experimental problem.
Alexei, perhaps this is a more tangible question. What about the impact of your research on physics itself? In other words, in what ways has your research advanced problems in physics that were much more difficult or did not seem easily solvable prior to the origins of quantum information?
I don't know. Throughout my career, I've studied some models, and I like simple models, which may be called toy models. And I found and studied several such models. This surface code is related to Hamiltonian. One can write the Hamiltonian corresponding to the surface code. That is not the same. I mean, the code that was implemented at Google is not the Hamiltonian. It's more like the computer science element in this idea that is used right now. But regarding the physics elements, there is this Tori code model that has not been implemented yet. There is another model on the honeycomb lattice, and people found some experimental realization, although it may not be exactly the same as in theory, but hopefully it's related. So I don't think I can help by making some hard problems easier. I just found some new types of problems and solved them.
Alexei, regardless of the commercial or social value in the future for quantum computers, maybe we'll get there, maybe we won't, but what are you most excited about for physics itself? What are some of the things quantum computers might help resolve that currently are not feasible?
Oh, yeah, that's a very good question. Quantum computers might help simulate complex physical systems. And one problem is high TC superconductors. High TC superconductors were discovered in 1986, if I remember correctly, a long time ago.
The Woodstock Conference.
Excuse me?
The Woodstock Conference.
I don't remember this name, but
yeah, at APS there was all that excitement. They called it the Woodstock Conference.
Okay, great. You know better than I. Yeah. So it's very exciting, but we still don't quite understand why they have these properties. And one reason it's hard to make a well-controlled experiment. We have real systems which include disorder, and interactions cannot be controlled easily, and not all quantities can be measured, and that's why it's hard to extract the needed data from the experiment. And people also do simulations on classical computers, but of course one cannot simulate a complex quantum system like that. One has to do some simplifications, and it's not clear whether those simplifications alter the results or they capture the essential properties. So doing a simulation on a quantum computer could help resolving all these issues and find which theories are correct. There are many theories and which are not correct.
Alexei, maybe it's as much a philosophical question as a scientific question, but what are some of the inherent challenges of working toward building a quantum computer using classical computers? In other words, to what extent do you need a quantum computer to build a quantum computer?
Oh, a quantum computer could simulate more complex quantum computers. Yeah, I don't know. We're not there yet. Yeah, we have to work with what's available right now.
But that is to say that you can use, obviously, classical computers. We do have at least the building blocks to get there, however rudimentary.
We can use classical computers. We can do some small-scale simulations of quantum systems on a classical computer, and that certainly helps. I didn't give another interesting example of what could be done with a quantum computer. In high-energy physics, and I guess John Preskill would give a better answer because he's done some real work on simulating field theories using a quantum computer. But one can come up with models of strongly interacting field theories that are hard to solve theoretically. And it would be very interesting to simulate them on a quantum computer, and that could help make some theoretical prediction regarding processes at very high energies.
Well, finally, Alexei, looking to the future, for my last question, you mentioned before that you might caution students that 15 years from now, there might not be funding in the field. So given where we are today, where there's so much excitement, there's so much resources, it's obviously a golden age for quantum information. What are some of the dangers or things to be mindful of to manage so that all of this excitement doesn't go away, even if these breakthroughs that are creating the excitement don't happen in the near term? In other words, how do we manage expectations and convey that patience is needed in order to see all of these things achieve fruition?
I don't know. I want to make a comparison with a different field, artificial intelligence.
Please.
And the idea of neural networks is pretty old. Artificial neural networks. It goes back to probably 1970s, if not earlier. And there was some initial hope to build an intelligent system using those networks, but it didn't work. And in general, work on artificial intelligence in 1960s and 70s didn't give very strong results. And then there was an artificial intelligence winter, as people call it. And only some 15 years ago, a new wave came, and those neural networks actually worked, and people are using them a lot these days. But the technology was not ready at the moment, I think. I don't know exactly what the problem was in that particular case, but with quantum computing, I hope that the technologies we already have, like superconducting qubits, are mature enough to build a working quantum computer. And in this case, the progress is likely to be continuous. But it might also be, it's like the same funding in some natural units was allocated to making a mechanical quantum computer in 1900s. And then the computer would have been built, I guess, given enough resources, it would have been built. But it wouldn't work very well. I mean, it wouldn't scale very well to solve real problems. And in this case, we know that better technologies just didn't exist in 1900s. And it might be the same situation with quantum computer. So it will turn out that making a scalable computer these days is just not possible. And one has to wait maybe decades before a better technology emerges. So I don't know how things will turn out.
It sounds, Alexei, like what you're saying is that a bit of historical perspective will serve the field very well in this regard.
Maybe, but it's hard to make predictions about the future.
Of course. Well, Alexei, on that note, it has been a great pleasure spending this time with you. I'd like to thank you so much for doing this.
It was my pleasure. Thank you.